Hello everyone, I am your instructor, Wang Shengda. In this lesson, we will learn about the impact of crystallization on polymer properties. Through this lesson, you will understand the effect of crystallization on polymer density, mechanical properties, and more, and will be able to compare polymer properties based on their degree of crystallization. Crystalline and amorphous polymers do not differ in chemical structure, but their physical properties are significantly different. Crystallization has a noticeable effect on polymer properties, including density, mechanical, optical, thermal, solvent resistance, dyeing ability, and permeability. For example, the properties of crystalline and amorphous polypropylene and polystyrene are completely different. Amorphous polypropylene is a viscous liquid, or a rubber-like elastomer, with relatively few applications. In contrast, isotactic polypropylene has a high degree of crystallinity, with a certain degree of toughness and hardness, making it a good resin. Amorphous polystyrene is a highly transparent, amorphous resin, mainly used in the production of foam materials. In contrast, isotactic polystyrene has a well-ordered structure, which can crystallize but has not been widely applied. Impact of crystallization on polymer properties. First, let's discuss mechanical properties. Effect of degree of crystallization on polymer mechanical properties. In addition to being related to the crystalline regions, it also depends on the amorphous region state. If the amorphous region is in the rubbery state, as crystallinity increases, intermolecular forces increase, leading to higher tensile strength, hardness, and elastic modulus. However, elongation at break and impact strength decrease. The polymer transitions from soft to hard. If the amorphous region is in the glassy state, as crystallinity increases, the molecular chains are closely packed. When the material is subjected to impact or tensile forces, the chain segments have no room to move. As a result, impact and tensile strength decrease, while modulus and hardness change little. The polymer transitions from hard to brittle. In the table, the properties of polyethylene with varying degrees of crystallinity are shown. As we can see, as the degree of crystallization increases, the tensile strength of polyethylene gradually increases, so does its hardness. Effect of crystallization on polymer density. In the crystalline region, molecular chains are arranged regularly. Its density is greater than that of the amorphous region. Therefore, as crystallinity increases, the polymer density increases. Extensive experiments have shown that the ratio of crystalline region density to amorphous region density in high polymers is about 1.13. By measuring the density of the sample, the degree of crystallization can be roughly calculated using the following formula. Effect of crystallization on polymer optical properties. The refractive index of a substance is related to its density. Therefore, the refractive index of the crystalline and amorphous regions in a polymer is obviously different. When light passes through crystalline polymers, refraction and reflection must occur at the interfaces of the crystalline regions. It cannot pass directly through. Thus, polymers with both crystalline and amorphous regions are usually opaque and milky in appearance. That is, crystalline polymers are typically opaque. Examples include polyethylene, polypropylene, nylon, etc. As crystallinity increases, transparency decreases. As crystallinity decreases, transparency increases. Polystyrene, poly, methyl methacrylate, etc. Completely amorphous polymers are highly transparent. How to increase the transparency of crystalline polymers. One method is to make the densities of the polymer's crystalline and amorphous phases similar. In this case, light will experience minimal refraction and reflection at the crystalline amorphous phase boundary. Another method is to reduce the crystalline region size. When the crystalline region size is reduced to below the wavelength of visible light, light no longer undergoes refraction and reflection. It can only pass through. For example, poly 4-methyl-1-pentana, which has larger side groups on the molecular chains. During crystallization, the molecular arrangement is not very tight. The crystalline region density is similar to that of the amorphous region. It is transparent. Transparent polypropylene is prepared using the second method. By adding nucleating agents, the number of crystal nuclei increases. The spherulite size decreases significantly, thereby increasing transparency. Effect of crystallization on polymer thermal properties as plastics. When not crystallized or with low crystallinity, the maximum service temperature is the glass transition temperature. When its crystallinity reaches above 40%, the crystalline regions are interconnected, forming a continuous phase throughout the material. Therefore, above the glass transition temperature, the motion of molecular chain segments is restricted by the lattice. It still does not soften. So, the maximum service temperature can be raised to the melting point. The melting point is higher than the glass transition temperature. Effect of crystallization on polymer solvent resistance and permeability. Because the molecular chains in crystals are closely packed and intermolecular forces are strong, they can block the penetration of various reagents and gases. Crystallization significantly affects a polymer's solvent resistance and permeability to gases and liquids. As crystallinity increases, polymer solvent resistance improves, solubility decreases, and permeability to gases and liquids decreases, such as polyethylene and polypropylene. These highly crystalline polymers are particularly suitable for making packaging containers for chemical solvents and reagents. Processing conditions affect the crystallinity, crystallization morphology, and other properties of crystalline high polymers, thus affecting their performance, such as polychlorotrifluoroethylene. If cooled slowly, the crystallinity reaches 85% to 90%. Impact strength decreases relative to the increase in crystallinity. If cooled quickly, that is, quenched crystallization, crystallinity reaches 35% to 40%. Impact strength is relatively high. To improve toughness, quenching reduces crystallinity to enhance impact resistance. Effect of crystallization on polymer properties. It is also closely related to spherulite size. For the same polymer, with the same crystallinity, but different spherulite sizes, performance varies. The smaller the spherulite size, the higher the tensile strength, impact strength, modulus, and transparency. So how do we control the spherulite size? First, control the formation speed. Rapidly cool the melt within a lower temperature range to generate smaller spherulites. Slow cooling generates larger spherulites. Second, use copolymerization. Disrupt chain uniformity and regularity to produce smaller spherulites. Third, add nucleating agents. This can generate small or even microscopic spherulites. In this lesson, we studied the effects of crystallinity on polymer mechanical properties, density, optical properties, thermal properties, solvent resistance, and permeability, as well as the effects of processing conditions and spherulite size on material properties.